Okay, welcome everyone to this continuation of quantum topology. Today I would like to tell you about duality in the categorical sense. And people usually call it pivotal categories or rigid categories. Rigid is a word I'm going to use for a while. And then pivotal is kind of the nice form of duality, if you want. And it really comes, at least from my point of view, from something like that has in diagrammatics that has singularities, and I'll show you what I mean by that. But it's kind of this mixture between duality and singularity. And again, as I said again, people call it pivotal or rigid. There are plenty of words people use for this because it's so important, has been rediscovered in many places, and people use different words for the same thing essentially. So I really like to think about the following picture. So duality. First I start with duality. So what is duality? Well, we could think of plain vector spaces. Vector spaces, everyone's friend. I hope at least. So at one point you learn in your life, you learn in algebra, and you think it's completely stupid, too difficult, and then eventually you grow up and you realize that linear algebra is the best thing ever. Computers love it. It's the best thing ever. And the standard examples I always have are linear algebra examples, right? Linear algebra, the best thing ever. Nothing ever gets as easy as linear algebra, to be honest. So linear algebra are really good. So in finite dimensional vector spaces, whatever, you have a vector space here. Let's zoom in. K to the 4, whatever, R to the 4, whatever your favorite symbol is. And you have a matrix, 4x2 matrix. And the dual matrix is literally just a transpose, a 2x4 matrix, and it goes the other way around, right? It's not 2x4, so it goes from k squared to k to the 4 in this case. The standard duality. So transposing matrices, the one obvious operation you can do on a rectangular grid is to just turn the grid, yeah, transposing the matrix. It's more like flipping, but anyway, you know what I mean. Transposing the matrix, and yeah, this is like the standard duality that people see. It's all over the place, and people love it and use it all the time, right? So duality doesn't change the object; it does this, right? But the dual vector space is only isomorphic to the vector space itself. They're kind of the same, but they're not quite the same. They're just kind of the same. And in categorical land, we always want to, distinguish that. So we will make a difference between the dual and the thing itself, but they will have still very similar behavior. And here you turn the arrows around here. And you can undo the process. That's kind of very important. You can undo the process by just doing it again in this case. Okay? So you have some form of inversion here. Yeah? And in my favorite example ever, in diagrammatics, so in one cop, duality would be just flipping diagrams. It's like the same as transposing matrices, and it does exactly the same. And in this case, actually, the dual is the thing itself, but in general, we don't want that, and we kind of assume, I wouldn't assume that this is the case. So we make a distinction between X and its dual. But keep in mind that, as I said again, they're like very similar in spirit. And as usual, you can undo what you have done. And I'll show you a nice picture of this undo what you have done in a second. Kind of a very important thing you do. But somehow we already had that when I was talking about duality earlier. So let's come to a slightly different perspective, a more diagrammatic type perspective on what this duality is. So duality, I would like to think about a singularity. Singularity? And singularity is one of these a little bit overused words. So if I just Googled singularity, and I think this summary is actually not good, is actually not bad. A singularity is a point where a physical or mathematical object is undefined, not really, often represented an extreme or breakdown of normal rules. So breakdown of normal rules. That's not quite how I see it. I will comment on that in a second. And indeed, if you search for pictures of a singularity, you mostly find black holes for some reasons. The Big Bang was a singularity. Yeah, the Big Bang here, a black hole here, here's a black hole, Big Bang again, and the universe since gets kind of less and less dense over time. very beautiful. Here's a singularity, a black hole type thing. So that's what you see if you search for singularity. What I really mean by singularity is more the mass type singularity. And there are again two versions of it essentially. This kind of undefined thing, yeah, where you have like here where you divide by 0 in this hyperbola, or a singularity. Ooh, this is a very tiny picture. The singularity. Can we make this bigger in geometry? Let's see whether we can make this bigger. Singular point, which is really a change. Yeah, singular point. Is there now a picture here? Apparently, oh, there you go. Singular point, where you have a change in behavior, right? So this is kind of a change in behavior here. Something special is happening at that point here. Something special is happening at that point. Everything else kind of looks the same. And then you have one point where everything changes drastically in some sense, right? So here you have drastic change of behavior. So this is type of singularity I'm talking about. Of course, it's kind of the same as this one where behavior drastically changes. When I really think about something where you have something very, very generic and then puff, something happens and everything is different. Think about the birth of a child. A very singular event. It's very quick actually. And changes everything. It just changes everything. That's what I would like to think about a singularity. Diagrammatically, I have something like this in mind, like a saddle. And there's an obvious point on the saddle which is different from all the others, where like the curvature changes from an upwards parabol to a downwards parabol, like this point here in the middle, right? Where you have something pointing up and then something pointing down, right? And kind of singularity, that's what type of singularity I think about. Something where behavior changes. Singularity is points of drastic change. And they're really important, right? Think about the birth of a child again. So most of life is like, all the same, boring, and then there are some very few singularities in your life. They're just like, oh, hopefully change everything for the better, but not always, because good things happen to bad people, and bad things happen to good people. Life is a lot of random shit. But anyway, so we kind of want to do the same. We want to allow in our diagram calculus a change of pace, if you want. Yeah? And this is often called Morse, or I will probably just call it Morse theory, and they will call the singularities Morse points, where something happens to the derivative in this little picture. Okay, so in kind of pivotal categories is kind of a mixture between duality and singularity, if you want, at least in the diagrammatics. And the formal definition is as follows. Again, we want to distinguish X from its dual in this case, and it gets even worse. We will distinguish a left dual and a right dual. In general, they might be different. Yeah, it's a bit annoying, but that's what we will do. So I get a right dual. I put the star on the right, and I have this monoidal category, which is literally just a datum of there exists an object and an evaluation and a co-evaluation, satisfying this undo, non-degeneracy, undo operation. You can undo this thing, right? Evaluation is an invertible thing. It's not really invertible because it gets from x tensor x star to trivial, but it's kind of invertible. It has this type of right inverse, and the other one has a left inverse. You kind of can invert what you've done, but not quite. Yeah? That's the concept of a dual. So dual is an object together with those two morphisms that are invertible in a certain sense. And the left dual exactly the same, just to draw everything the other way around, right? So now the star is on the left. Look at this x dual, x dual, x. So you have two options. You call one of them left dual. You call the other one right dual. And I will draw these pictures a little bit nicer in a second. But essentially I call them a zigzag relation because it goes like that, right? Zigzag. And you straighten it out. Yeah, you nicely straighten it out. And I said again, it's like an inversion of the operation of evaluation or the operation of co-evaluation. A left or right inversion. Cool. What you should have in mind is dual vector space and evaluation map. So dual vector space is the map of linear functions, so you can just evaluate your vector on it, and that's the evaluation map. And there's something that's called the co-evaluation, which just is the sum of certain things. We'll see that in the next week. Not super difficult. But why do I call that Morse points? Because eventually I would like to draw the following diagrams. So I use the following trick. Let's do that maybe a little bit zoomed out. I use the following trick. I draw X as a line, as I usually do it, but I put a little orientation on it. And by that I mean, whatever it's pointing upwards, it's X itself. Whatever it's pointing downwards, it's actually the dual. So I distinguish the X from its dual by an orientation. And let's assume that left and right dual doesn't make any difference, they're the same. Okay, so then I can draw my evaluation map going from X to X star as a little cup. The Morse point thing, right, where something changes because you go to the monoidal unit. Can do it the other way around, co-evaluation, evaluation, whatever. And since I assume that X is X star, as left is right, I have all of these maps. And now it completely makes sense why I have all of these maps. That's exactly the 4 possibilities how I could draw a cup with an orientation. And the non-degeneracy relations here will be just, oh, you can pull it straight. That's literally it. That's literally it. You just need to be careful left or right, whether you can pull it straight to the right or straight to the left. But if they're the same, you can just pull it straight. And this is kind of a very nice diagrammatic way to think about, well, now we have Morse points where something changes because you drastically change your strength and go down to the monoidal unit, but they're somehow also invertible operations because you can just pull the string straight. And what people usually call, as I said, the non-degeneracy condition is exactly the straightening of diagrams. Anyway, I hope you enjoyed these singularities and this video, and I also hope to see you next time.